In the previous video, we were expressing the volumes of these solids generated by rotating some region about the non-coordinated axis. We calculated the first one, the second one, and we stopped in the third one. I already checked that these were the correct answer. Now let's continue. We have not committed any mistake yet, any silly mistake. The other are no, we're not going to commit. That could be just distraction error. Well, anyway, let's continue. Here we calculate the radius of the solids of the discs in the region between y equals 1, y equals square cube x, and the y-axis. We are rotating it around y equals 1. So we saw that the radius was 1 minus the value of the function. So this was our radius. So the area of each disk is pi times 1 minus cube x squared. The volume would be this times delta x, and the volume of this solid of revolution will be the defined integral from, we are going from the y-axis, so from 0, from I equals 0 to y equals to x equals this point. This point is the intersection between y equals 1 and y equals cube x. So we have y equals well, we have 1 equals cube x. So x is equal to 1. So from 0 to 1 of all this stuff. Pi of, let me put it of the volume of each disk, and the volume of each disk is pi times 1 minus cube x all square. Alright, let's continue. Now, the volume of the solid generated by rotating the region enclosed by x equals 3, y equals 2, y equals 1 over x minus 1, about the line x equals 3. This is the graph. The region will be x equals 3 is this, y equals 2 this, this will be the region. So we will rotate this around this line x equals 3. So we will have a solid, if you visualize it like this. This will be the solid. So now we will do cross sections in the y direction. Will be this. This will be our discs now. So the volume of each disc will be pi times r squared times the y. Now the y of each disc is dy. So we need to put now everything in terms of y. So first, what will be the radius? The radius is the distance between x equals 3 and the function. One way you can do it is you subtract all this, you subtract this from this, and so you will have this radius. So let me put this y equals 1 over x minus 1 in terms of x. So we put this here, and we have x minus 1 is equal to x minus 1 is equal to 1 over y. So x is equal to 1 plus 1 over I. So to this we are going to subtract this from y equals from x equals 3. So the radius will be 3 minus 1 minus 3 minus 1 plus 1 over y. So this would be 1 over y plus 2. Now the area would be this square times pi. The volume of each disc would be this times the y. And now the volume of all the discs will be the defined integral. Let me leave the integrations at the end of 1 over y plus 2 all square dy, and let me take out the pi. So we are going from this point to this point. So it is enclosed by the line y equals 2, so we are ending at y equals 2, that is here. That's our upper limit, y equals 2. And our lower limit is when the curve y equals 1 over x minus 1 intersects the line x equals 3. So that will be the y value when x is equals to 3. So here you would have 1 over 3 minus 1, so it's 1/2. So from would be the defined integral from 1/2 to 2 of 1 over I plus 2 all squared dy times pi. This will be the volume of this solid. The next one is the region enclosed by y equals 2 times x minus 1 all squared. We will rotate this about y equals 2. So here we have y is equals to 2. This is our curve, so is this region. And we will rotate this around y equals 2. So we would have a solid that looks something like this. So if you do cross sections of this, you will see these discs like this. So the volume of each disc will be dx delta x times the area. Now the area is what's the radius. The radius is, you can think as the difference of the distance from y equals 2 and this graph, because if to this graph, to this value of y, we subtract the value, for example, we subtract the value of the sorry, I put wrong the discs, so for that is not concordating. This is our region. The discs are, and this will be this solid generated, but the regions will be something like this. So now would be delta x times dx times pi r squared. Now pi r squared is, what's the radius? You know, the radius is half of the diameter, half of all this distance. So is the distance from y equals 2 to the curve. To the curve, for example, here, if you subtract, let's say we will find the radius of this disc, that radius is this. So if we subtract 2, that is all this distance, 2 minus the value of y equals 2 times x minus 1 all squared, you will have this distance, and that will be the radius. So the radius is r is 2 minus 2 times x minus 1 all square, all this square. The area will be all this square times pi. And now the volume of each one of these would be this times delta x. The volume of our solid would be the defined integral from, we're going from here to here. So these are the points in which the graph y equals 2 times x minus 1 all square is intersecting to y equals 2. So this value will be, we have 2 equals 2 times x minus 1 all square, divide everything by 2, I have 1 square root 1, and I put this, so it's x equals 2. So the defined integral from, sorry, I have was 1 equals x minus 1 all square. Taking the square root is plus minus 1 equals x minus 1. So if I take 1, x would be equals to 2. If I take minus 1, x would be equals to 0. So this go from x equals 0 to x equals 2. Here I didn't put it very well. This intersection should have been here. Of minus 2 times x minus 1 square, all this square, pi delta x. This is our volume. The next one, the region enclosed by y equals 1, x equals 4, y equals the square root of x plus 1. This region is rotated about y equals 1. So first our region is x equals 1, x equals 4. This is our region. So this will be rotated around y equals 1. So about y equals 1, I think that is kind of similar to that one that we did. Well, so we will have this solid. This will be our region. The cross sections would look something like this. This will be our discs. So the radius of each disc is the difference between the distance of y equals 1 and the graph root of x plus 1. So because this was our region given, we will take the distance from we will subtract 1 to this region. So we will have the radius is equal to square root of x plus 1 minus 1. So the radius is just square root of x. If you're asking why sometimes we subtract the line from the curve and sometimes the other way around, it depends on if the region, for example here that we are rotating about some y equals some value, it depends if the region is above or below. Because look, if we were to rotate this around the x-axis, our volume or our solid of revolution would look something like this, and will be all of this will be our solid of revolution. That's one point. The next one that is following the first one is you want the distance from this curve. The radius is the distance between this curve and the line, or between this line and this curve, but you don't know what this curve is, because this curve is not the complement or the other way. That is not y equals minus square root of x plus 1. That would be if you rotate it around the line equals 1. Maybe we do a video explaining this in more details. Or actually, I think that we already did a video. Anyway, now, so root of x, square root of x. So the area is pi x. The volume will be pi x dx, and so the volume of all the these this will be the defined integral from here to here. Here the last one is x equals 4, and the other is the intersection between y equals 1 and square root of x plus 1. So if I put 1 here, square root of x will be plus or minus 1. We know that minus 1 isn't, so it's in plus 1. So we go from, yeah, did I do that? Oh, don't, sorry. If I put 1 here, is 0 equals square root of x, and so this will go from 0 to 4. Next is the region enclosed by y equals square root of x plus 2, x equals minus 2, y equals 1, y equals 3, about y equals x equals minus 2. So the region enclosed is, this is y equals 3, this is y equals 1, this is the curve root of x plus 2, so is this region. If you rotate this around x equals minus 2, you will have something like this. More or less, this will be our disc, our solid, and so the cross sections will look something. Well, this will be our discs. The volume will be, now will be the delta y times pi r squared. Now, which is pi r squared? Pi r squared will be the radius is the distance from x equals minus 2 to the graph. That is, what's the value? Let's say, what's the value of x in just this, in the graph square root of x plus 2? Well, let me solve for x. So x would be square y minus 2. So let's say we want this value when we are, let's say, at y equals at y equals 2 or whatever, or y equals 2. Yeah, because we're going, yeah, when y equals 2, x is equal to 4 minus 2, x is equal to 2. X would be equals to 2, let's say here. Now, the distance is not x equals 2. The distance is all this plus this. So it would be this plus this. Now, so the radius would be r, would be equal to the function that is defined in y terms, square y minus 2, plus this distance. This distance is 2, or you can think it as minus 2, minus negative 2. So plus 2, and so you have that the radius is just square y. So the area is pi y to the 4th power. The volume would be this times delta y. This will be the volume. And now the volume of our solid would be the defined integral from, we're going from here to here. So we are going, when the graph y equals x plus 2 intersects the line x equals minus 2, this will be this point. So x plus 2, so let me substitute minus 2 here. So this will go from 0 to here, and this is y equals 3. So from 0 to 3 of pi, I will put the pi here, y to the 4th power dy. Just 3 more. The other one would be, or actually, if you want, we will continue this in the next video.